Hi class, this week we are going to talk about two-way ANOVA. If you remember from last week, in one-way ANOVA, there is one dependent variable that is either interval or ratio, and one independent variable that is either nominal or ordinal. The key difference between one-way ANOVA and two-way ANOVA is the number of independent variables. In two-way ANOVA, there are two independent variables, both of which need to be categorical, meaning they must be either nominal or ordinal. An example will help clarify this concept. Let's see the Tennessee State Superintendent of Instruction asks the Director of Educational Research to investigate whether there is a gender difference in scores on a standardized teacher examination for senior education students across 4 subject areas: vocational education, physical education, English, and mathematics. Pause here for a moment and ask yourself, how many variables are involved in this research question? What is the dependent variable? What are the independent variables? The dependent variable is students' score on a test. There are 2 independent variables. One is gender, the other one is subject area. Gender is dichotomous because it has 2 values, male versus female. Subject area, aka major, is a nominal variable with 4 categories. We already mentioned they are vocational education, physical education, English, and mathematics. To help you understand the data structure better, let's define some notations. Let's call gender the role variable and label it as J, where J equals 2. We call it the role variable because it defines the 2 rows in this table. One row is for male students. The second row is for female students. Similarly, let's call major the column variable and label it as K, where K equals 4. The dependent variable, the scores, is presented in the 8 cells created by the 2 independent variables. Can you tell why there are 8 cells? Because there are 2 rows and 4 columns. 2 times 4 gave you the 8 cells. Because each student has a score, so we can tell there are 4 students within each cell. For example, there are 4 male students in vocational education. There are 4 female students in English. Altogether, there are 32 students, 16 males, 16 females. There are 8 students sampled from each of the 4 majors, with 4 males and 4 females in each. The grand mean is the average of all 32 scores. In addition, there are 6 marginal means. First, we have 2 marginal means for the variable gender. The 16 scores of male students have a mean of 35.81. The mean of the 16 female students is 36. They are labeled as x1 dot bar and x2 dot bar. respectively, because male has j equals 1 and female has j equals 2. Why are they called marginal means? Because we ignored the second independent variable, major, when calculating them. The existence of the second variable is only acknowledged by this dot as a placeholder indicating a two-way design. For the variable major, there are 4 marginal means, as the 4 subject areas divide the sample into 4 groups. They are labeled as x.1 bar, x.2 bar, x.3 bar, and x.4 bar. Here, the dot serves as a placeholder for the first independent variable, gender. Because major is the second independent variable, the dot goes in front of the values 1, 2, 3, 4. Each of the 8 cells has a mean. It's called the cell mean. For example, the mean for the 4 female students in mathematics is calculated as the sum of 35, 45, 48, and 44 divided by 4, which gave you 43. In one-way ANOVA, we perform a hypothesis test, comparing the average values of the dependent variable across the groups defined by the one independent variable. In two-way ANOVA, since we have 2 independent variables, the analysis becomes more complex. We conduct 3 hypothesis tests. They are the test of the main effect of the first independent variable, the test of the main effect of the second independent variable, and the test of the interaction effect between the 2 independent variables. For each test, we follow the same 5 steps of hypothesis testing. The first step is to state the hypothesis. To test the main effect of the first independent variable, we know that this variable has j values returning in j marginal means. So the null hypothesis states that all j marginal means are not statistically different. Keep in mind that the hypothesis tests are always about population parameters. So it's mu1 dot equals mu2 dot equals all the way to mu j dot. We use mu for population mean, not x bar. And the non-directional alternative hypothesis is that not all j means are equal. Note that this is the general form of the hypothesis. Based on it, you get the specific hypotheses for your particular research question. For instance, in our example, gender is the first independent variable and has j equals 2. So the null hypothesis should be mu1 dot equals mu2 dot, saying there's no significant difference in the average scores of the male and female students. The alternative would be mu1 dot not equal to mu2 dot. This set of hypotheses is similar to a one-way ANOVA test, except that the dots in the notation remind us of the presence of a second independent variable. For the test of the main effect of the second independent variable, the hypotheses are similar. Since the column variable has k values, the null hypothesis is mu dot 1 equals mu dot 2 equals all the way to mu dot k, stating that all k marginal means are not statistically different. The non-directional alternative hypothesis is that not all k means are equal. In other words, at least one of the means is significantly different from others. Be clear that the dot as a placeholder for the row variable goes in front of the numbers in this case. In our example, the column variable major has k equals 4. The null hypothesis states that all 4 marginal means are equal. Mu dot 1 equals mu dot 2 equals mu dot 3 equals mu dot 4. And the alternative hypothesis states that at least one of the means is different from others. Finally, the third set of hypotheses is for the test of interaction effect between the two independent variables. Simply put, the test of interaction effects checks whether the effect of one independent variable is consistent across different levels of the second independent variable. The null hypothesis states that the interaction effect is 0, meaning after the main effects of the two independent variables are removed, the cell means stay comparable to the grand mean. Otherwise, there is significant interaction effects between the two independent variables. The format of the hypothesis for their interaction effects stay the same regardless of which question you're working on. After completing the hypotheses, let's move on to step 2, in which we choose the alpha level for the 3 sets of hypotheses. Let's use alpha equals 0.05 for this example. In step 3, we need to run the ANOVA test in SPSS. The information from the SPSS output will enable you to complete step 4, in which you make a decision whether to reject or fail to reject the null hypothesis from step 1. Steps 3, 4, and 5 will be demonstrated and explained in another video. So this concludes this video. Thank you for watching.